Good morning. I am Dr. Sunayana Ghodgaonkar and I would be taking a lecture on computer aided drug design, and I am associated with SS Zondare College of Pharmacy. I'm an associate professor from Department of Pharmaceutical Chemistry, and I would be taking a lecture on computer aided drug design. This is a 1 week course. This is an add on course for the benefit of the students, and upon completion of this course, students will be able to to understand different molecular modeling techniques, understanding the process of docking. I will also take a case study of the software that I have used, and there will be summary and conclusion. So, what it will include is aim, reference, introduction, techniques of molecular modeling, docking, and summary. Okay, so the aim is computer aided drug design, and these are some of the references that I have been using. Okay, so we would be doing molecular modeling studies, particularly two-dimensional quantitative structure activity relationship is particularly important, and then after that we also do three-dimensional quantitative structure activity relationship. What are descriptors used in one dimensional and zero-dimensional quantitative structure activity relationships would also be then understood. Okay, so we are doing measuring QSAR attempts are done because we are just trying to quantify the change in the structure, change in the substituent of a particular compound causing change in the biological activity. So we are trying to quantify just that change. Okay, so if a particular substituent is changed in a given structure, then the biological activity would change. That is the assumption on which QSAR equation exists. Okay, so we are basically using computational chemistry and we are using statistics so as to generate an equation, so that a particular equation will predict activity for a given set of compounds, given series of compounds, and then only those compounds would be synthesized. Earlier it used to happen that lakhs of compounds were synthesized, of which only 4 5 compounds showed very good activity. Now we don't need to spend those lakhs of rupees on synthesis of compounds and then identifying the activity of compounds. We would rather see to it that we would be able to predict with the help of software compounds having drug-like activity, and then we would do its clinical trial studies, and further we would go for synthesis of these compounds for manufacturing of those compounds on larger scale. So initially we predict the activity of the compound with the help of QSAR design or computer aided drug design. Then we perform docking techniques by which we understand how does the compound act in vivo by actually interacting the compound with protein, ligand, or enzyme, and then we would be able to say, okay, this particular compound is having very good docking. This is the compound that has been indicated by the QSAR equation to have greatest of activities, and hence we can use this compounds for further synthesis. So we are actually cutting the cost of chemicals that is required for synthesis of compound having optimum pharmacological activity. Okay, so we are basically trying to also uh, put the physicochemical parameters or the physicochemical properties of a given compound. We put them in the form of numerical descriptors, which is nothing but the numerical representation of the physicochemical properties of the compounds. I mean, these physicochemical properties are coded in the numerical descriptors. Okay, and we use these numerical descriptors. Okay, and then we show the relationships between that is quantitative relationship between the physicochemical properties of a particular compound and biological activity of the compound. Now, QSAR, it is helping to rationalize. This helps to rationalize the process, and the fundamental hypothesis of QSAR states that the biological activity of a series of compounds can be quantitatively correlated to the physicochemical parameters or structural properties of the compound. So, what are the two objectives of QSAR? The two objectives include development of a robust QSAR model. Okay, robust QSAR model will prevent any kind of chance correlation. Okay, we don't want a model that is full of errors. Okay, and this QSAR model should have a specified chemical domain For example, if we are using a series of benzodiazepines, then you should have a particular benzodiazepine domain, okay, chemical domain for prediction of activity of untested compounds. And it should also have an information tool. It is an information tool, sorry, uh, uh, concerning the mechanisms causing a given biological activity, that is informative by extracting significant patterns in descriptors related to the measured biological activity. So, what are the physicochemical parameters that is responsible for a particular type of activity? That information should be also given by a particular QSAR design. Now, what is QSAR? It is the most uh, frequently used technique, and it is given in the mathematical form as activity is the function of physicochemical or structural properties. Okay. Now, what are the parameters in designing an equation of a QSAR or designing a model for a QSAR? The most important factors include the lipophilic parameters, the polarizability parameters, electronic parameters, steric parameters, and the miscellaneous parameters. Okay, the lipophilic parameters include, of course, the partition coefficient, which is a very important parameter because mostly the drugs are hydrophobic. Okay, and they must be hydrophobic because your lipoprotein membrane is hydrophobic. So it's an important parameter, partition coefficient, then pi substitution constant. Then you have polarizability parameter that includes molar refractivity, paracore related to temperature. Then you have electronic parameters, particularly Hammett's constant and dipole moment. Steric parameters include the Taft's constant, where you talk more about the bulkiness of the compound. Okay, and then the miscellaneous parameters, like for example, molecular weight, geometric parameters, and so on. Now let's talk about lipophilic parameter, or we talk about the partition coefficient. Is basically lipophilicity is the partitioning of a drug between an aqueous and a non-aqueous phase. We particularly use non-aqueous alcohol octanol because it is having structure similar to your lipophilic membrane, and therefore we are using this drug as a reference for partitioning of the drug in the organic phase. Okay, so B is drug in octanol upon drug in water. So if we draw an equation, then we that is we test the values of log P against log of 1 by C. Then what we get is a straight line. We are using particularly log values because only log values help us get a straight line. Okay, therefore we are using log values. Okay, so log 1 by C. For example, we say the equation for this particular line, okay, is log 1 by C is equal to 0.75 log P plus 2.30. So if the graph is extended to very high P log values, that means if the number of alkyne groups, for example, are added to an extent that the log P values become very high, then this straight line will get converted into a parabola curve. Okay, so that simply indicates that the activity has now decreased. To ethyl group, addition of alkyl group up to certain extent to increase the hydrophobicity and the activity of the compound is appreciated, but then you cannot add alkyl groups to an extent that the activity is lost, because more hydrophobic the compound becomes, the more it sticks to the cell membrane, as it cannot penetrate the cell membrane. So we have to see that the substitution done or the substituents attached, they are attached only up to a certain value or up to a certain limit, beyond which the straight line gets converted to parabola. And if you can see, the parabolic equation can be of the type when log 1 by C is equal to K1 log P plus K2 log P K plus K3. So you see, when P is small, then it is dominated, the equation is dominated by the log P value, and when P is large, then log P square dominates, and so activity decreases. Okay, so this was the first important parameter for hydrophobicity. The next parameter for hydrophobic compounds is the pi substituent constant or hydrophobic substituent constant. This pi substituent constant was defined by our scientist Hansch, and Hansch is responsible for this QSAR technique today, and he has done great contribution to computational chemistry. We must thank scientist Hansch for this. So he and his co-workers, they have defined this pi substituent by the equation log px minus log ph, where px and pH, they represent the partition coefficient of a derivative of the parent molecule and the partition coefficient of the parent molecule. Okay, so where x is the substituent that has caused the change. Okay, now, a positive pi value will indicate that the pi substituent has higher lipophilicity and than hydrogen, and the drug favors the organic phase. And the negative pi value will indicate that the drug has lower lipophilicity and it favors the aqueous phase. Okay. So now let's move towards our next parameter known as the electronic parameter. Now this was done by scientist Hammett. Hence the name of the equation is Hammett equation, and this is a very useful tool for measuring the extent of charge development of on an activated complex. Yes, the molecules should be completely neutral, but yes, an activated complex can have a charge. Okay, and what, how is that charge developed? If you attach a substituent at the meta and the para position of a benzene ring, then it will change the ability of that aromatic ring. As you know that you must have performed the experiment in which you took some benzoic acid and to it you added some water and then you added some KMNO4 and the color never changed. The reason because the color did not change is because COOH is an electron withdrawing group, and this will deactivate the ring. Okay, so this Hammett's constant, it will indicate whether a particular substituent is going to deactivate the ring or is it going to activate the ring. So this activating and deactivating of the ring is again quantified. Okay, and this is converted into an equation. Okay, and this was done by Hammett. Okay, here we see the equation that you already have an aromatic ring which already has a methyl group which can be para to and there could be another methyl group which is para to the original methyl group, or you can only have methyl group all alone in the para position. No, okay, and then you have a bromo group which is again para to methyl group, and a bromo group that is in the meta to the methyl group. Please have a look at the equation. The methyl group is para to the original methyl group. You have one aromatic ring which has single methyl group. Then you have another methyl group attached at the para position. The alkyl groups are electron donating and they will activate the ring. Whereas the bromo group, you see, they are halo groups. They are electron withdrawing groups and they will deactivate the ring. So, and you will see bromo group at both the para and the meta position. When the bromo group is at the meta position, it is electron withdrawing bromo group. But when it is in the meta position, then the electron withdrawing activity is greater because it is near the methyl group. Okay, so Hammett's constant is not for the ortho position because this ortho position is only going to cause steric hindrance. Okay, so we are not considering ortho position here. Okay. Okay, substituents are only attached to meta or para position, so they do not sterically interfere while attachment interfere with the site of attachment of the phenyl ring. So this Hammett's constant is given by sigma. This sigma is log of Kx upon K benzoic acid, where benzoic acid is the parent molecule and K is the constant for acidity constant for benzoic acid, and Kx is the acidity constant of the substituent that is associated with benzoic acid. Okay, so this X is bringing some change. Now we go to when will the electron, where will the equilibrium shift when Kx is greater than K and K benzoic, and when Kx is less than K benzoic. See, if Kx is greater than K benzoic, then the sigma will be positive. Okay, that means log Kx minus log K benzoic, then value of sigma will be positive. Okay, and if it is smaller, log kx is smaller, then the sigma value would be negative. Hammett's constant will also take into um, account both resonance inductive effect, also it also mesomeric effect. Thus the value will depend whether the substituent is para and meta. Ortho is not measured due to steric effects. Then we come towards the next constant, also known as the steric substitution constant. Okay, steric substitution constant is basically measuring the bulkiness in the group. Okay, it represents and hence its effect on the closeness of contact between a drug and receptor site. Although it is very difficult to quantitate steric substitution constant. The steric substitution constant is represented by tough steric factor, as this was discovered by scientist staff. Okay, here he has described the hydrolysis of methyl ethanoates. You can see how a methyl ethanoate is getting hydrolyzed, and he has given the equation es is equal to log of kx minus log of ko, where x is the substituent on the ester, and so it is and ko is the original parent ester. Okay, so kx is the represents the hydrolysis rate of substituted ester, and ko represents the hydrolysis rate of parent ester. So it is assumed that the values of ES obtained for a group using the hydrolysis data are applicable to other structures containing that particular group. Okay, so that means you can use different substituents, X substituents on methyl ethanoate and compare its activity with methyl ethanoate. Okay, so substituted methyl ethanoate, hydrolysis of substituted methyl ethanoates can only be compared with hydrolysis of methyl ethanoate as the parent compound. You cannot compare chalk and cheese. Okay, so if you are using methyl ethanoate, then you cannot compare it with ethyl acetoacetate. You have to compare it with methyl ethanoate only. Okay, so molar reflectivity measures the volume occupied by an atom or group. Okay, so equation includes molar, molecular weight, density, and index of refraction. You also have word loop steric parameter. Here, a computer program itself uses bond angles, van der Waals radii, and bond lengths. Now we talk of 2D QSAR models. Okay, particularly 2D QSAR models are developed using Hans equation. Okay, and there were two other scientists, Free and Wilson. They also generated their own equation. We'll have a look at that. Okay, now talking of Hans equation. Okay, it's a linear free energy approach. Hans is using all the parameters, including the lipophilic, electronic, and steric parameter, and then it is giving two types of equation, the linear equation and the parabolic equation, and the dependence E is on lipophilicity on the biological activity, where log BA, where that is log of biological activity, is A log P plus B sigma plus CES plus constant. Okay, that is called, that will give you a linear equation, and when the too much of log P is increased, then the activity will be in the form of parabola. I mean, it would be non-linear, and the equation would become A log P plus B log P square plus C sigma plus DES plus E. Now you see A, B, C, D, E. These are the constants of generated in by a regression equation. Okay, this model was further improved by Kubini. He said that instead of saying log of B, he took log of 1 by C concentration less is equal to A of B log P plus C log BP plus 1. Okay, so what are the steps for involved in application of the Hansch model drug design? So first you have to take the lead compound, then select substituents, then synthesize, evaluate the biological activity, then determine physicochemical parameters and formulate regression equation, and then evaluate the model. Okay, then you should do correct interpretation of the model, and then application of QSAR design should be done so that it makes most potent and less toxic molecules. Okay, now Now, what are the requirements? Data requirement. What is the data requirement? The biological activity. For it, you should know that the biological activity is sedation in case of diazepines, benzodiazepams. Okay, activity should be sedation. Okay, so first biological activity should be known. Then a data set of at least more than 20 compounds, because if you take lesser compounds, then there will be chance correlation. Okay, कुछ भी equation generate हो जाएगा and we will feel that, oh, this is showing very good sedative activity. That should not be the case. Okay, you cannot design any compound just because you're generated some equation. It is not generation of just some equation, it is generation of a equation of a robust molecule, robust design that can help in designing of novel molecules having drug like activity. Okay, so for QSAR to be valid and reliable, the activity of all chemicals covered must be elicited. Okay, you already should know the biological activity. Okay, and then you can use this by building a model. Okay, and biological activity can be in any form. The continuous response, that is MIC, minimum inhibitory concentration, IC50, ED50 values or percent inhibition values, and categorical response, whether the given substituent makes the compound active or inactive. Okay, so in order to have confidence in QSAR, biological data should be of at least 20 molecules. Okay, now preferably these molecules should be tested in the same laboratory and by the same biological assay method with wide range. Okay, with uniform distribution of activity data, and activity should be well defined in real number, not less than 100 or greater than 1000. No, it should be in real number. Activity should be in real number or in a particular class. Okay, say for example benzodiazepine, that class. Okay, molecular descriptors. What are molecular descriptors? They are numerical representation of chemical information. Okay, physicochemical parameters, basically numerical representation of physicochemical parameters. Okay, within molecular structure via mathematical procedure. Okay, types of QSAR is based on the dimensionality of the molecular descriptors used. For example, if you are using 0D QSAR, then you use molecular formula, molecular weight, and number of types of atoms. Okay, if you're using 1D QSAR, then you talk about functional groups, rings, bonds, substituents. These are 1D representation. Okay, then when you talk about 2D QSAR, then you talk about total path count, molecular connectivity indices, particularly atoms bonded in the molecule, both the type of bonding and interaction of particular atoms. So that is all about 2D QSAR. Then in 3D QSAR, you have molecular surface, molecular volume, other geometrical properties. Okay, the 3D QSAR. Also in 4D QSAR, you talk about conformations of the compound or any other experimental condition. So how do you design a QSAR? You should have a test set and a training set. So in training, you make two sets, the test set and the training set. You select some compounds you think they may have activity, and you let off some compounds thinking they already have good activity. Then you convert it into two sets, one with for whom you are testing, and one with whom you are letting off thinking that it has good activity, and then you are trying to connect both the sets. Okay, so what are the methods for division into test set and training set? I personally use manual selection. This is done by visualizing variation in chemical and biological space of the given data set. Okay, visualizing on looking at the compounds. Okay, and what is the variation that is has to be done by certain knowledge of chemistry. Then random selection, this method will randomly select molecules. Sphere exclusion method is a good method. This is a rational method for creation of test and training sets. It ensures that the points in both the sets are uniformly distributed and with respect to chemical and biological spaces. Then you also have other methods like the experimental design, full factorial design, fraction factorial design, onion design, cluster analysis, principal component analysis, self-organizing maps. These are some of the types of uh, other methods. Then you have variable selection methods also. There are hundreds of molecular descriptors. It is very difficult to really choose what descriptors you should use. Okay, and not all can be used because there are thousands of descriptors that determine the biological activity, and hence it is very important that on the you use those descriptors which would be required for that equation. Okay, then you therefore you use a variable method to select the descriptors. The variable selection method could be divided into stepwise forward backward, and stepwise backward method. I personally use stepwise forward backward method. Then you have a stochastic variable selection method. These methods are based on simulation of various physical and biological processes, and this method creates model starting from randomly generated models and or modifying the models by using different processes operations such as perturbation crossover to get better models. Okay, so stochastic variable selection may include simulated annealing, genetic evolutionary algorithms, modified particle swarm organization, and artificial colony system. This stochastic method is more for genetic engineering kind of studies, not more for drug molecules. Okay, then use of statistics in QSAR. Various statistical tools are available to analyze the data of molecule and to correlate molecular structure or molecular descriptors with their corresponding biological activity. A suitable statistical method coupled with a variable selection method allows all analyzing all the data to establish a QSAR model with a subset of descriptors that are statistically significant in determining the biological activity. So, what basically I want to claim here is that we are using both computational chemistry and statistics to generate an equation that will predict the activity for our test compounds that we have taken in the test set. So, test and set and training set. Okay, so that is how you are using statistics for predicting the activity of compounds. Okay, and these statistical methods can be divided into linear method and non-linear method. Okay, so in statistics the correlation is established between the dependent variables, that is your biological activity, and independent activity independent variables, that is your molecular descriptors, which are nothing but physicochemical properties that are made converted into numericals. Okay, so the linear method fits a line between selected descriptors and the non and activity, as compared to non-linear method which fits a curve between the selected descriptors and activity. Now, the statistical method to build QSAR model is based on type of biological data. So what is the biological data you feed in, and then that will only determine the statistical method to build a particular QSAR model. Following are the commonly used statistical methods. Okay, there are various statistical methods depending on the data to build a QSAR model. So until now we were talking only about the computation chemistry. Now we are talking about statistics. So we have categorical dependent variable, discriminant analysis, k nearest neighbor, logistic regression, decision trees, and SIMCA, of which k nearest neighbor classification is a very good method. Okay, then you have continuous dependent variable, multiple regressions, again a very good method. I have personally used it. Principal component regression, continuous continuum regression, partial least square regression, I have used this also. K nearest neighbor, I have used it. Some very good methods: multiple regression, k nearest neighbor, and partial square least square, very good methods. Now you, after that you evaluate the model, okay, using various statistical measures. Okay, for evaluation of the model. Okay, and then most commonly used measures are enlisted below. Okay, the model can be evaluated. You get a straight line, you get a total count, pathway count, then you get a graph, and you finally get an equation which will have indicated by n number of molecules. Then you have the number of descriptors. Okay, statistically n by 5 descriptors in one model. Okay, then you have df or the degrees of freedom, r square is coefficient of determination, q square is cross validated. Then you have predicted r square, the value should be greater than 0.5 for external or test set. Then standard error of estimate should be as low as possible. F test is for statistical significance of the model. Okay, higher the is better for same set of descriptors and molecules. Of course, this should be higher. That only then only it will give clearly an idea of what kind of molecules should be designed. Then F prob alpha error probability, they should be smaller. And then you have a Z score which is calculated by randomization. So less the randomization, higher the randomization, it is better. Then you have best rand square, that is how rand q square, that is again randomization. This should be as low as compared to q square. So q square is your basically cross validation, and then randomized q square is your randomization in cross validation. So that should be low. The randomized less randomized is the cross validation. Greater activity, greater is the activity. Okay, then alpha statistical significance parameter by randomization, again randomization should be as low as possible, should be less than 0.01. Okay, now after this we talk about the free Wilson method. um, so Free and Wilson, they are these scientists contributed to this method, and they said that the biological activity is basically the summation of different substituents. Okay, so BA, that is biological activity, is equal to summation of AIXI plus U. So biological activity is the average contribution of the parent molecule, and AI is the contribution of each structural feature. Okay, whereas X denotes the substituent, and X can be 1 or 0. In 1971, Fujita and Band further simplified the free Wilson equation, estimating that the activity for non-substituted compounds of the series, and they postulated that the logarithm of activity can be brought, can bring the activity in a straight line. Always log values will make a straight line. Therefore log BA is equal to GI summation of GI xi plus mu. So in this equation, mu is defined as the calculated biological activity of the unsubstituted parent compound of a particular series, where G represents the biological activity of contribution of the substituent. So Xi represents the value of one of the substituent is present. Okay, so Xi is the substituent. Okay, which and its value can be 1 or 0. But the Hans equation particularly is even used today. So how do you discover a compound? You first do the compound screening, then you do lead identification, then lead optimization, then what is the target identification. For example, you talk of anti-cancer activity, then epidermal growth receptor factor is the enzyme, is one of the enzymes that is expressed more in tumors. So say if your uh, uh, target is EGFR, then you should identify that target, then target validation, and then you will do drug discovery studies in silico modeling, that is 2D 3D QSAR along with docking. After that you will do toxicology studies of the molecules that are predicted, and then you will go for animal studies. Okay, so following steps are performed for molecular modeling. Basically, you build a set of molecules for QSAR analysis, then calculate descriptors, then you make a fitness plot, then you build a QSAR, and then the plot a graph of activity versus predicted activity. So there are various paid and free softwares available for QSAR. Personally, I had used software VLife, but you also have the software Central Regional Desk Methods, Education at Dela, Formation, POI software, Compass software, Compa and COMSIA, particularly for 3D QSAR, Schrodinger, MOE, USCF, Chinese Autodoc. You also have normal Autodoc. Then Autodoc is used for docking, and this is USCF Chimera software. But Autodoc is particularly used for docking. Even I had used Autodoc for docking for my PhD studies. Okay, so what basically you do, this is a case study by VLive. You open an existing folder where you have drawn the structures of different compounds. You have also calculated IC50 values. So you import those structures using software, convert that CDX file into SDF file, and then to 3DF molecule, that is mol2 file. Then pick tools, then you calculate descriptors, you go to tools, and then you go to QSAR from main menu, and then you check WS from the QSAR, open to new border, and a dialog box pops out, and open an existing folder containing a set of molecules stored in the separate files in the folder. Now this is how you do it. How it the window pops out is something like this. Okay. Once the window pops out, you will select some descriptors, and then you will further proceed and consider them as dependent. Okay, because okay, then this is you will use the method partially square method. You will see the number of rounds of iterations is 10. More the iterations, better is the result. Minimum 10 iterations are necessary. Then here is what you get is known as the fitness plot. Okay, well, it will also give total pathway count, but fitness plot is very important. Okay, then you come to 3D QSAR. Particularly, mostly used software is comparative molecular field analysis (COMPA) Tripos. Okay, you build each molecule using modeling software, and then you identify the active conformation of each molecule, identify the pharmacophore, and place that pharmacophore in the lattice of grids. This is your lattice of grid. Then this is the way you place a compound in the grid. You have a contour also. You have a probe atom. You will see this is the probe atom. Place it in the grid. This is how you get a table given by the software. Okay, you get an equation, okay, of the same. We have used the method partial least squares. And then after 3D QSAR, you come to docking. Okay, this is computational simulation of candidate ligand binding to a receptor. Docking means the compound should actually sit on the enzyme or ligand or protein, whatever you say, and it should completely integrate with the enzyme. That is the layman's language. But in computational chemistry, you call the same thing as docking. Okay, so docking can be between protein and small ligand, protein and peptide, and protein and protein nucleotide, also protein and molecule. Okay, types of docking can be either rigid, both the receptor and the ligand are kept rigid, or flexible. There is flexibility between receptor or the ligand or both. This is how exactly the docking occurs. You see that it completely fits the black piece, completely fits the maroon space, and also the blue one. Also, the third structure is also a very correct structure. It should exactly fit in the space. It's like a jigsaw puzzle. Now you see that you should know the receptor structure, okay, for docking. This is generally an X-ray crystallography structure or an NMR structure, and it can be taken from RCS website or protein data bank, PD bank, and okay, for proteins especially. And if the structure is not available, then you try to build a structure using homology modeling or comparative modeling. This depends upon the relationship or between a particular protein structure, depend on which another protein structure can be built with target protein, and at least one structure of the target protein should be known. Okay, then once the enzyme fits with the molecule, then you will select which pose that the molecule gives, and what is the probability of that molecule fitting into that enzyme or the receptor or ligand or protein, and then what is the best pose by which the molecule can fit in the enzyme. Okay, and this is done by trial and error method, and molecules that have energetically good poses, that pose is selected. Okay, a pose of correct conformation and flexibility is selected. A thorough search of degrees of freedom, okay, is done, and after that scoring functions are applied. Okay, once the scoring functions are applied, then the best pose is identified with the dot score. So this is how computer aided drug design helps in drug discovery, and it is currently used all over the world. And I just wanted to give an idea to BPharm students about these novel techniques, as they are not part of the syllabus. Okay, they are part of an elective subject which most students don't even take. But it's a very interesting topic, interesting subject, and we should concentrate on this. Uh, Thank you to one and all. Okay, the road is long and deep, and I have 2 miles to walk before I sleep. Miles to walk before I sleep. I thank you all for paying attention towards my slides and towards my audio. Thank you very, very much for all your time. Thank you. Peace out.